Welcome to the last session of PQCrypto 2022. In this session, we have 4 talks on quantum algorithms, attacks, and models. If you have any questions or comments, please leave it in Julie. Okay, let me start the first one. The first talk is Quantum Attacks on SLAE Message Structure by Shupeng Mao, Ting Guo, Peng Wang, Lei Hu, and then Shupeng will give a talk, please.
Thank you for your introduction. Hello, everyone. My name is Shupeng Mao. I'm from State Key Laboratory of Information Security, CES, and I'm glad to introduce quantum attacks on message structure. In classic, Aram Yuan et al. Considered that Fistel structure had the same security as Lamsey structure, and they proposed quasi-Fistel structure. Actually, in classic, 3-round Fistel structure and Lamsey structure are CPA secure, and 4-round Fistel structure and Lamsey structure are CCA secure. But in quantum, Jinbo Ido showed that 3-round Fistel structure can be attacked by using Siemens algorithm in quantum. But Luo et al. Showed that 3-round Lamsey structure can resist quantum attacks of Siemens algorithm. So this led to natural questions. Do Lamsey structure and Fistel structure have the same number of rounds that can be attacked in quantum? And can the attacks be extended to quasi-Fistel structures? During the different existing conclusions, then it is possible to re-attack the Lamsey structure in quantum. So we focus on the quantum attacks on Lamsey structures. First, we introduce some definitions. The R-round Lamsey structure, AR and BR. The S-round of Lamsey structure, LM'(R) as this. AR equals AR-1 XOR. FR AR-1 XOR BR-1, and BR has the same form as AR. For I is less than R, the S-round of Lamsey structure LMI as AI equals sigma AR-1 XOR FI AR-1 XOR BR-1, and BI has the same form as BR. The sigma has the isomorphism property. Sigma and X map to sigma X minus X are both permutations. And in this paper, we use the instantiated Lamsey structure used in Fox, and the sigma as sigma XL XI equals XR, XL XO XR. And here, we give a new definition of the square buckets of A and B. AB represents the highest n/2 bits and the lowest n/2 bits, respectively. And here we give a quantum chosen plaintext attack against 3-round Lamsey structure. This is a 3-round Lamsey structure, and the inputs are x1, x2, and x3, x4. The corresponding outputs are y1, y2, and y3, y4. The process is shown in this figure. And if we let the inputs of the whole process x1, x2, x3, x4 as this, and we can construct a periodic function G1 based on x1, x2, x3, and y1 and y3 with a period S as this. So we can compute S by using Siemens algorithm in ON quantum queries. So now we have a periodic function G1 and we have a period S. So we can construct a quantum CPA distinguisher by using Siemens algorithm in ON quantum queries. And we give a quantum chosen Ciphertext attack against 4-round Lamsey structure. This is a 4-round Lamsey structure, and this is the inverse of the 4-round Lamsey structure. The attack process is shown in this figure. and we input x1, x2, x3, x4 to the 4-round lambda structure and get the corresponding output y1, y2, and y3, y4. We XOR n1, n2, n3, n4 to y1, y2, y3, y4 to get the corresponding z1, z2, z3, z4. And we input z1, z2, z3, z4 to the inverse of the 4-round lambda structure and get the corresponding output x'1, x'2, x'3, and x'4. So for the input x1, x2, x3, x4 of the whole process, let's input as this. And let n1, n2, n3, n4 as this. So we can construct a periodic function G2 based on x'1 and x'3 with a period S as this. So we can construct a quantum CCA distinguisher by using Simmons algorithm in ON quantum queries. And we also give a quantum key recover attack on 4-round lambda structure. This is a 4-round lambda structure, and the inputs as x1, x2, and x3, x4. The corresponding output as z1, z2, and z3, z4. Now we get the key k4 of f4 as key. Now we have the output of the 4-round lambda structure z1, z2, z3, z4. And the guessed key. So we can compute the intermediate parameters y1, y2, y3, y4 of the 3-round lambda structure through the reverse of the last round of lambda structures. This is the process and shown in this figure. We denote y1, y2, y3, y4 as y1k, y2k, y3k, and y4ks. Let the inputs as this. And we can construct a period function G3 based on x1, x2, x3, and y1k and y3k. If the key is guessed right, then G3 is a periodic function with a period S as this. So we can give a quantum Grover-Mix-Simon attack with O(n) times 2 to the power of R2 quantum queries in quantum CPA. So according to our result, 3 or 4 rounds lambda structure can be attacked by using Simmons algorithm in quantum. This is the same as Fistel structure. So the next question is, can the attacks be extended to quasi-Fistel structures? Now we focus on the quantum attacks against quasi-Fistel structures. First, we introduce a definition combiner. A function gamma is a combiner if for yz, x mapped to x, gamma xyz is a combiner, and for xz, y maps to gamma xyz is a combiner. And we denote the combiner as gamma x star y vertical bar z. According to Aram Yuan et al., the combiner of Fistel structure is x, or y, and our result shows that the combiner of the instantiated lambda structure is sigma x, XO, the inverse of sigma y, XO, the inverse of sigma z. And we introduce the B branch R round quasi-Fistel structure. For the input x, PQ are permutations. For the input x equals x1, x2 to xb, we can calculate z0, z1 to zb minus 1 by calculate px. And we can calculate zi plus b minus 1 as zi minus 1 and zi to zi plus b minus 2 and fi zi to zi plus b minus 2. And we get the output y as the inverse of q, zr plus 1 to zr plus b minus 1. We call a quasi-Fistel structure is balanced if b equals 2 and unbalanced if b is greater than 2. For the S round of balanced quasi-Fistel structure, we denote Zi-1 as X. We denote the Fi-Zi as Y and Zi as Z. So we consider the case that the combiner of the balanced quasi L2, L2Y, XOR L3Z. And here we give a quantum chosen plaintext attack against 3-round quasi-fistal structure. And this is a 3-round quasi-fistal structure. The inputs are Z0 and Z1, and the corresponding output are Z3 and Z4. The process is shown in this figure, and let the input as X and alpha B. And we can construct a periodic function G4 based on Z3 with a period S as this. So we can construct a quantum CPA distinguisher by using Siemens algorithm in ON quantum couriers. And we give a quantum chosen Ciphertext attack against 4-round quasi-fistal structure. This is a 4-round quasi-fistal structure, and this is the inverse of the 4-round quasi-fistal structure. The process is shown in this figure. We input Z0, Z1 to the 4-round quasi-fistal structure, and we get Z4 and Z5. We XOR M1 and M2 to get Z'4 and Z'5. We input Z'4 and Z'5 to the inverse of the 4-round quasi-fistal structure, and we get Z'0 and Z'1. Let's input as this, and M1, M2 as this. So we can construct a periodic function G5 based on Z1 and alpha B with a period S as this. So we can construct a quantum CC distinguisher by using Siemens algorithm in ON quantum couriers. Finally, we would thank to the reviewers for their constructive comments during the review process. One of the reviewers pointed out that the combiner gamma of balanced quasi-fistal structure does not need to be all linear. After our verification, only L1 need to be linear. And if the combiner of gamma equals L1x XOR FYZ, where L1 is linear and F is a function, there exists a quantum CPA distinguisher against 3-round balanced quasi-fistal structure and a quantum CCA distinguisher against 4-round balanced quasi-fistal structure. To sum up, we show that Lamses structure and fistal structure have the same number of rounds that can be attacked in quantum, and the attacks can be extended to quasi-fistal structures. Thank you all.
Thank you for your interesting talks. So now I have one question. Did you have tried any attack on round 5?
I think round 5 is secure under the quantum attacks by the Siemens algorithm. But I think maybe some other attacks methods can attack 5 rounds, but it still need to try.
Okay. Any questions? So currently there is no question or comment in Julep. So okay, thank you very much.
Thank you.
Let's move to the second one. Okay, the second talk is sponge-based authenticated encryption security against quantum attacks by Christian Jensen and Patrick Struck. Patrick will give a talk. Hi, Patrick.
Hi, yeah, thank you for the nice introduction. As you said, so my name is Patrick Struck from University of Regensburg, and this is joint work with my co-author Christian Jansson from TU Darmstadt. Let me very quickly start with the motivation. So we have asymmetric and symmetric cryptography. And for asymmetric cryptography, we know, due to Shor's algorithm, the main motivation behind this conference that we need post-quantum cryptography. based on quantum hard assumptions. And the other thing we have is with Grover's algorithm that we usually know we need to double the output length of hash functions in order to be secure against quantum adversaries. For symmetric cryptography, on the other hand, there was not so much done yet, and mainly the assumption was like for symmetric cryptography, we only need to double the key length in order to protect against Grover's algorithm. But very recently at this year's Eurocrypt, there was work that showed that actually better attacks might be possible even for symmetric cryptography. So explicitly analyzing security also for symmetric primitives is important, which gives the motivation behind this work. And here we look into sponge-based authenticated encryption, and in particular into the scheme SLAE that we developed with Jean-Paul de Gabriel in 2019, which was designed to resist side channel leakage and is closely related and also inspired by another sponge-based scheme called ICEP. And the core difference between SLAE and ICEP is that for SLAE we rely on T-sponges, meaning for the sponge-based construction you see here at the bottom, the underlying function rho, this will be a random function, whereas often for the sponge constructions, this is assumed to be a permutation. So SLAE by itself actually follows a more generic construction, which we call the FGHF prime construction. So it follows the encrypt then MAC paradigm. So we have an encryption scheme and a message authentication code. And we decompose the encryption into a fixed input length function f and a pseudorandom generator g, and the message authentication code into a vector hash function h and another function f prime. And then with the input, what effectively happens, we first encrypt the message using the encryption scheme, and afterwards also produce the tag for the ciphertext. Now, when we look at the concrete sponge function, so this is the encryption part here, where the first part here, this is this function where we first feed in the nonce of the scheme. And then for the second part, minus the final XOR, this is the PRG part of the construction, to which finally the message is XORed in order to produce the ciphertext. And for the message authentication code that is displayed here, we also get this first part here, which corresponds to the sponge-based hash function. So we start with the nonce as one input, then absorbing the associated data blockwise, followed by absorbing the ciphertext here, where there's a special input separation to demarcate when the absorbing of the ciphertext take place. And then in the second part, we have again the sponge-based function, which now takes the hash function as the input. Now coming to the security of SLAE against quantum attackers. So we consider two models. The first one is the commonly known post-quantum or Q1 model. So we have a quantum adversary, and in this case, we grant the quantum adversary quantum access to the so-called offline oracles, but classical access to the online oracles, which in case here means the offline oracle is this public transformation rho that underlies the sponge construction, whereas the online oracles are basically all the oracles that are provided by the challenger who is in possession of the secret key of the construction. The other model that we are then considering is the quantum or Q2 security. And here the difference is now that also to the online oracles, we can grant the adversary quantum access by assuming that also the challenger has quantum computing power. And for this part, we only consider the encryption part of the construction, so not SLAE as a whole, but SLENC, the underlying encryption scheme. And then we have several different security notions that we need to consider. In this setting by Bonnet and Zentry from 2013, by Gayadoni, Hösing, and Schaffner from 2016, as well as from Musayebi and Sheikh also from 2016. Let me start with the post-quantum security. So, as I mentioned earlier, this scheme was initially designed to withstand side channel leakage. So from this setting, we have a security proof in the leakage setting that basically shows that the security of SLAE as a whole boils down to the security of the four underlying primitives, the functions f and f prime, the pseudorandom generator g, and the hash function h. And what we show is that dropping the leakage part, we also easily get post-quantum proofs for this. So also the post-quantum security of SLAE in the Q1 setting boils down to the post-quantum security of the underlying components. which means now this is what we have to finally show for this post-quantum security for F, G, and H, as well as F prime. And for this, so for the pseudorandom function, the core effectively relies on the one-way to hiding lemma, the following bound. And similar we get for the pseudorandom generator, also relying on the one-way to hiding lemma, we can bound the security. And then finally, for the hash function, we can use prior work by Tchaikovsky et al., which gives this slightly more complex bound, but also shows security for this construction. And this as a whole then, with the other proofs, gives a post-quantum security of the whole AE scheme. Then coming to the quantum or Q2 security of the construction. As mentioned earlier, there are several notions that we have to consider here, in particular the three. And one thing initially here is for all these schemes, the randomness is always assumed to be classical. And in our case, this would be then the nonce. So we opt for the following. We decided to allow the adversary to also specify some nonce, potentially in superposition. But to deal with that, we decide that the challenger will just measure this register to make sure that the nonce is a classical value. And then to deal with the repeating nonces, the challenger can just reject the query if a nonce repeats. And this shows, well, if we restrict this to classical setting, this is equivalent to the normal setting we have for nonce-respecting adversaries that will not repeat any nonces. Let's start with the first security notion. This is the INDqCPA security notion by Bonnet and Zentry. And in this notion, the adversary gets access to two oracles. There's a CPA oracle for learning queries and a challenge int oracle to actually show that the adversary can break the scheme. And what Bonnet and Zentry in this model do, they grant the adversary quantum access to this CPA learning oracle while restricting the challenge int oracle to be only invoked classically. So for the CPA oracle, we can ask a superposition of messages and get back the superposition of ciphertext. Whereas for the int oracle, the adversary just can send two messages and get in return the encryption of one of the two messages. And to show, well, we can show security for the underlying encryption scheme in this model, mainly following the post-quantum security, because in prior work, Anand et al. Showed that for stream ciphers, so meaning we produce the key stream to which then the message is XORed to get the ciphertext, that post-quantum security easily carries over to this INDqCPA security here. Yeah, and that's how we achieve INDqCPA security for the SLAE. Then the other case, these are the stronger qINDqCPA security notions, one by Gaiadoni et al., the other one by Musayebi and Czech. And here the crucial part is now also they allow quantum queries to this challenge int oracle. And in the case of the first notion, the adversary is allowed to specify two messages that it sends to the oracle, and in return it gets back the encryption of one of the two messages. And this is a bit simplified, so that actually you can do it like this. There are more details, which I'm skipping for sake of simplicity here. And in the other notion by Musayebi and Czech, the adversary only can choose one message and a ciphertext register. And in return, it will either get back the encryption of the message or the encryption of a permuted message, and has then to distinguish whether the actual message or permuted message was encrypted, which reflects more of a real or random security notion, whereas the left notion is of the form left or right encryption. But also here, essentially from a text that were developed in these two papers already, where they specified the notion, can also show that you can break SLAE with respect to both notions by also exploiting the stream cipher property of the encryption scheme. So let me wrap up and conclude with some open problems. So we were looking into the security of this sponge-based authenticated encryption scheme SLAE against quantum attackers. We showed security in the post-quantum or Q1 sense, and we also analyzed it in the quantum or Q2 sense, where here we showed that we also achieved this INDqCPA security by Bonnet and Zentry, whereas for the stronger qINDqCPA security notions by Gaiadoni et al. And Musayebi and Czech, we do not achieve security. So an open problem would be to extend these results to ISAP. And if you recall from the beginning, I said for SLAE, we have a random transformation underlying the sponge construction. And this is the part that allowed us to rely on the one-way to hiding lemma. Whereas for ISAP, if we have a public permutation, we can no longer rely on the one-way to hiding lemma, because the adversary would also get access to the inverse of the permutation. Yeah, that's mainly the problem, the difference between the P sponges and the T sponges. And the other thing, as said from the design, initially the scheme was designed to withstand side channel leakage. And so far we have a proof against the side channel leakage, and now one for the post-quantum security. And an interesting thing would now be to combine the two things to show that even a quantum adversary, if it gets some classical side channel leakage, cannot break security of the scheme. And this concludes my presentation. I'm happy to take any questions.
Thank you for the interesting talks. Maybe now there is no questions on Julep, so it must be a naive questions. But can you extend? Can you apply your techniques to hash function itself with sponge constructions?
Well, that's not really what we were doing. So, like, this is the thing. There was the work by Tchaikovsky et al. From PQCrypto 18, I think, and they looked into the post-quantum security of sponge-based hash functions. And I think that the crucial part there, they also looked, and that's the nice thing that we could use, into the T sponges. So this was a crucial part here. Whereas then, well, this left still open, like proving post-quantum security for SHA-3, where you would use with Ketchuk the P sponge. And I think there were initial works, but I think so far we're still don't have like a convincing proof at this time for SHA-3 with the P sponges.
Mm-hmm. Okay, thank you. Okay, let's move to the next talk. So actually, Patrick, you will give the first talk, but we need to exchange the third one and fourth one. So please go ahead for the next talk. So the next talk is on quantum ciphertext indistinguishability, recoverability, and OAEP by Julian Kramer and Patrick Strock. Patrick will talk again.
Yeah, thanks again for the introduction. Yeah, I don't need to introduce myself, but yeah, this is then joint work with Juliane Krämer, who's also from the University of Regensburg. So like what we also had from the previous talk, in the quantum setting, we can consider different levels of security. And here, roughly, we can divide it into the following three: classical security, post-quantum security, and quantum security, where classical security means both the adversary and the users only have classical computing power, in which case queries that the adversary can make are restricted to be classical. Then for post-quantum security, we assume that the adversary has quantum computing power, whereas the users have still classical computing power. And here, this was the thing also from the previous talk, that now we grant quantum access to the offline oracles, anything that the adversary can compute locally, like hash functions, when we model them as random oracles, whereas classical access is a restriction for all the online oracles, where the adversary needs to interact with the user that only has classical computing power. And for quantum security, we also assume that the end users might have quantum computing power, and then we can also grant this quantum access to the online oracles. And this is the setting we consider in this work. And in particular, we are here interested into quantum security notions for public key encryption schemes. And at the moment, we have three different security notions for this. And the first one is the qINDqCPA security notion by Bonnet and Zandri. And here, they restrict the challenges for the adversary to still be classical, but they allow quantum access to the decryption oracle in this case. And this notion is of the form left or right, so send two messages, one of the two messages gets encrypted, and you receive back the ciphertext. And one thing, this notion is always applicable to encryption schemes. The next notion is the qINDqCPA security notion by Chevalier, Ebrahimi, and Wu from 2020. Here the difference is that they now allow the challenges to be quantum, And this is a notion of the real or random form. So either it gets the message that is queried gets encrypted, potentially in superposition, or the message is first permuted and then encrypted. And also this notion is always applicable to any public key encryption scheme. And the third one is the, also called qINDqCPA security notion that we developed in prior work together with Tommaso Gagliardoni. And this also allows quantum challenges, but instead it is of the left or right form, so also sending two messages and only receive the encryption of one of the two messages. And the crucial thing here that this notion is not always applicable to public key encryption schemes. And this is also the scope of our work on the applicability of this security notion. Before we can jump into the notion, quick recap on the quantum operators, because we need this. So here we can see what we call an XOR operator, which is like the canonical way of implementing functions on a quantum computer, where we have the two registers X and Y for input and output. And then the function is evaluated and XORed into the second output register, while the input register remains unchanged. There's an alternative way of implementing functions on a quantum computer, and this is what we call the in-place operator, which were first introduced by Kashevi et al. In 2002. And here this operator just takes some input X and directly transforms this register into f of X. And due to the quantum mechanics, we can only realize reversible functions for this operator. And in particular, what this prior work by Kashevi et al. Showed is that these operators are not always efficiently realizable. So they are stronger than the counterpart on the left side. And these operators are the building block we use for this qINDqCPA security notion from last year. So we have our adversary and the challenger. The adversary will send two messages to the challenger. Challenger will flip some bit B at random. Based on this, we'll discard one of the two registers received from the adversary. And then it applies this in-place operator here, which takes some randomness to encrypt, chosen by the challenger, and the message register MB, and maps this to the randomness and the encryption, so the ciphertext of this particular message under this randomness. And then the challenger will send back the ciphertext register to the adversary. So the core part in this prior work, as mentioned earlier, it is not obviously clear that you can realize this operator. And in prior work, we showed that this works for schemes that are perfectly correct, so no decryption failures. But here the construction requires both keys, so both the public and the secret key. And the other one we showed for recoverable public key encryption schemes, and then we could show that you just need the public key of the scheme. So more details here on the recorded talk. But very briefly, this recoverable public encryption scheme means that these are schemes that if you know the randomness that was used to produce a ciphertext, then you can decrypt this, the ciphertext to the message without knowing the secret key. So in this sense, the random coins give you enough information to recover the message from the ciphertext. So the question that we now ask in this work here is, are there public key encryption schemes for which this qINDqCPA security notion cannot be defined when we restrict challengers to only know the public key? And the motivation behind this is, if we take the challenger, that is usually one of the encrypting parties. And for public key encryption schemes, that's the person who would only know the public key. So like this construction we have here with that requires both keys. This seems from a practical perspective not really the interesting one, but more interesting would be if the challenger only knows the public key. And we know there are schemes, namely all these recoverable schemes, for which it turns out most schemes are indeed recoverable public key encryption schemes. So, well, based on this property with the recoverability and decryption failures, we can classify public key encryption schemes, what we did in prior work. And so, as said, the interesting one for our question are now these non-recoverable schemes, because for the recoverable ones, we know that we can realize this operator. And now we're looking for one where we cannot do this. So the question is, are there any non-recoverable public key encryption schemes? And so far, we only know via some generic transformation that we developed based on a trapdoor permutation that we can convert recoverable schemes here into the non-recoverable ones. And in this work, we refine this classification and show that actually there's something in between what we call equivalent recoverable schemes. And this prior transformation from last year only maps into this equivalent recoverable schemes. And we can easily come back to this recoverable setting. So the question is still open. Are there any non-recoverable schemes? Except now we do not know any schemes so far. Okay, and now looking for non-recoverable schemes, we come to the OAEP construction. So this is a construction that takes a trapdoor permutation and converts it into a public encryption scheme, and looks here as displayed on the right-hand side. So we have some message and some random coins, and we do this 2-round Feistel construction to get these values S and T, and then apply the trapdoor permutation F in order to get the ciphertext. The security for the OAEP construction is based on the partial domain one-wayness of this trapdoor permutation F, meaning given this ciphertext C, it should be hard to find this partial pre-image S. When we come to the recoverability of the OAEP construction, here we show, if we take the same assumption, assuming that F is partial domain one-way, then the OAEP construction is not recoverable. And in particular, what this means, so like you would be given the ciphertext C, and you would be given additionally from the recoverable property this randomness R. So obviously from the randomness R, you can compute the value G of R. But then still to find the message M, you would need to compute the XOR of G of R, which you know, with this value S. So still, if you would be able to recover the message, you would already break this partial domain one-wayness by finding the value S here. On the other hand, it also turns out that this partial domain one-wayness is crucial. Just assuming, well, from C, it's hard to recover both S and T. This is not sufficient. And you can think of a construction where it's easy to recover S, but it's hard to recover T. And then if you know S and from R you compute G of R, then you can easily recover the message M. Okay, so far so good. We now know that the OAEP construction is not recoverable, but this so far only rules out the one construction for the quantum operator that we know, but it doesn't mean that, well, there's no other way to do it. And to deal with that, we introduce a new security notion. So first, here's this partial domain one-wayness written out as a game. So, well, some inputs S and T are chosen, then the function is applied, and the adversary is asked to find this partial pre-image. And we construct a variant of this notion where we give the adversary an additional value R here, which directly corresponds to, from the OAEP construction, hashing S and XORing it with T. And what we then show is for this, well, if the function achieves this partial domain one-wayness, it also achieves this slightly stronger notion with the extra hint. And here the idea is that the value R doesn't really help because, well, if you can derive some information, you also already found the value S and solved the partial domain one-wayness. And now based on this, we show that we cannot construct this in-place operator that we would need for our quantum security notion. And for sake of contradiction, we assume that you can realize this in-place operator for solely knowing the public key, and that the underlying function achieves this slightly stronger notion of partial domain one-wayness. Then we can show if you know this or can construct this operator, you can also construct the inverse operator. And then with a bit more construction, we get this following circuit here. And for this, we can show that this construction would break you this partial domain one-wayness or the stronger variant, thus contradicting our assumption. And in particular, we know both these in-place operators up here by assumption were only constructed using the public key. And also for these two XOR operators, G and H down here, we also do not need the secret key. So this would be one construction that only relies on the public key. And with this, we can show that, well, for OAEP, we cannot construct this necessary quantum operator for this qINDqCPA security notion. So let me conclude. So we were focusing on the applicability of this qINDqCPA security notion, and we focused on this setting where the challengers are restricted to only know the public keys. For this, we showed that the OAEP construction is non-recoverable, and also being the first scheme that we are aware of that achieves this or does not achieve recoverable property. And then based on this, we also showed that this mandatory in-place operator cannot be constructed for the OAEP construction with this restriction only knowing the public key. For future work or open problems, the question would be, are there more non-recoverable public key encryption schemes? So far, we only know the OAEP construction. And the other thing, as I mentioned earlier, there's another quantum security notion by Chevalier, Ebrahimi, and Wu. And at the moment, we only know that these two notions are incomparable. So I think a unified quantum security notion, or better understanding the relation between the two, where they are equivalent, this would also be an interesting question for future work. And with this, I'd like to conclude my presentation, and thank you very much.
Thank you for the nice talk. So I'm a little bit confused. So could you a little bit summarize about how can we use OAEP securely in quantum A? So
good question. At the moment, we don't. So it's theoretically we would need this trapdoor permutation, for which we don't have so far any. I'm not aware of any instantiation on some quantum hard assumptions. So for sure, with RSA, you could argue now, well, we cannot define it, but who cares? We already know that RSA will be not even post-quantum secure. But who knows, maybe at some point someone comes up with a realization of this trapdoor permutation from some post-quantum assumption.
Oh, okay. Let me check the tulip. No. So thank you very much.
Thank you,
Patrick. And then the next one is by Ursan Ebrahimi. And then
you are now unmuted.
Maybe we have some problems. Okay, let us just refer to the video on the website. So for the last talk, we have some technical problems. So let us refer to the video on the website, and then let us conclude here. So, okay, thank you everyone for participating in PQCrypto 2022 until the end. I appreciate all the speakers for their great talks, and then Tanya Lange and other organizers for organizing the conferences. It did a very good job. So now let me pass the mic to Tanya for some remarks from steering committee of PQCrypto. Thanks. Tanya? Hello?
Had a chance to follow.
Okay.
All right. So I'm now speaking here with my double hats on. So first of all, as a general chair, I'm thanking all the speakers for timely delivering all the videos and the slides and for being here. I'm very sorry to the last speaker because we spent the last 45 minutes trying to debug and something didn't work with the audio. So please, audience, please watch his video as linked from the schedule. It's 23 nice minutes. Unfortunately, we can't show you any live version. Now I'm putting a different hat on, and I'm speaking now as the as a member of the steering committee of PQCrypto. And as such, I would like to thank our program chairs for putting together this program. So thank you very much, Yoonhee. Thank you very much, Thomas, for putting together this great program and, well, making these 3 days happen. I hope we're going to see some more discussions on the Zulip server. So this server will stay up because I'm seeing lots of people from different time zones watching the live feeds at different hours of the day. So for the next few days, I recommend that everybody still show up every once in a while on the Zulip to see whether there's a new message, answer, well, pose your own questions. And it's nice if you could add the chair in the speaker in there so that then they get an email notification so that they know that something is happening. Okay. Still taking a breath. So thank you once more for the nice program here, Yoonhee Jeon and Thomas Johansson. This ends PQCrypto 2022. Now, the typical way is the conference is over, but there's the next conference. So PQCrypto 2023 will happen for sure. We're not 100% sure yet where. The current plan is to move slightly back. I mean, we used to have PQCrypto before summer. Now we're thinking of gradually moving back. Something like August would be good. We are in talks with potential organizers. So please stay tuned. We will announce as soon as we can. And we all hope that by then the pandemic will be over and we can meet in person again. But we also understand that, well, there's probably still some need for having an online presence. So we're going to take this into account. It's something as a steering committee we're very aware of, that organizing something after COVID means, yeah, having more backup options, having more plans. But that also means it's somewhat more complicated to run it, which means it's somewhat more complicated to find people to run it. With that, thank you all for participating. Hope to see you again next year. Bye.
Thank you.